Hello and welcome back to Forge College. In our last lesson, we wrapped up our setup and next steps for Solana Cloud. Today, we are jumping back into the Ethereum ecosystem to tackle the principles of gas optimization. If you write smart contracts long enough, you eventually run into a wall. The fees required to actually run your code are incredibly high. Minimizing those transaction bills is the core challenge every Ethereum developer has to face. Here is a quick animation to help picture the problem. Imagine an ultra-greedy, highly literal restaurant kitchen. In this kitchen, you are billed for every single physical movement the chef makes. If the chef takes a step, opens a drawer, or chops an onion, a receipt prints out and adds a specific dollar amount to your total bill. That kitchen is exactly how the Ethereum Virtual Machine, or EVM, operates. The EVM is our mechanical chef, and the tiny execution steps it processes are called opcodes. Every individual opcode consumes a specific amount of gas. That gas requirement directly translates into the transaction fee the user has to pay out of their own wallet. The secret to controlling these costs comes down to one fact. Opcodes do not share the same gas weight. Some actions are incredibly cheap, while others are astronomically expensive. Real gas optimization means strategically picking the absolute cheapest sequence of opcodes that still achieves the exact same result, rather than just writing fewer lines of code. To make the right choices, developers have to constantly balance two drastically different categories of opcodes: math and storage. First, we have math opcodes. These handle basic arithmetic and logical operations, like add and mul for addition and multiplication. This diagram shows what math operations look like in our kitchen. Notice the orange plus sign dropping onto the cutting board. This represents the chef standing perfectly still, just dicing vegetables right in front of them. Because these arithmetic operations happen locally in temporary memory, they require very little effort. In terms of gas, they are incredibly cheap. Then we have the dangerous category, storage opcodes. The main culprits here are SLOAD, which reads save data, and SSTORE, which writes new data. When you use a storage opcode, you are forcing the chef to drop their knife, walk all the way across the massive kitchen, and heave open a 10-ton deep freeze vault door. The cost difference is steep for a reason. Storage opcodes are huge gas hogs because they don't just use local memory. They permanently alter or query the long-term global state across the entire Ethereum network. Knowing the difference between the cutting board and the vault is important, but things go wrong fast when we introduce the hot path. That's the section of your code that runs the most frequently, usually the inside of a loop. This flowchart illustrates a very common developer mistake, putting a storage read and a storage write directly inside a heavily trafficked loop. Let's say you are simply counting up by 1. The opcode sequence requires an SLOAD to fetch the current count from the vault, an ADD on the cutting board to increase it, and an SSTORE to walk it back to the vault. In a high-level coding language like Solidity, that looks like a harmless single-line equation. But underneath, the compiler is mapping it to those massive EVM vault operations. If that equation is inside a loop, your gas bill skyrockets. The chef is dragging the heavy vault doors open, slamming them shut, and doing it again for every single repetition. Hiding expensive state opcodes inside a hot path acts as a negative multiplier. It destroys your code's efficiency by charging you the highest possible price over and over again. The solution comes down to a deliberate trade. We can intentionally run extra, cheap math operations to entirely bypass those expensive storage operations. This redrawn flowchart shows the coding technique that makes the trade work: caching. Instead of going back and forth, caching means you do one single SLOAD at the start. You pull all the data out of the heavy vault once and store it temporarily in an orange basket on the cheap cutting board, which is your local memory. Now, the chef can stay at the counter, doing all the repetitive math over and over again without ever taking a long walk across the kitchen. When every calculation is finished, the chef takes the final tally and performs one final SSTORE to lock it back in the vault. You can even use specific unchecked blocks in your code when your math is provably safe from overflowing. This skips the EVM's automatic safety checks and saves you even more of those cheap opcodes. By explicitly caching data locally, you accept a few extra steps at the counter so you can completely avoid dozens of globally expensive trips to the vault. That is true opcode efficiency. This checklist outlines the 3 immediate steps you can take to lower your gas costs right now. Rule 1. Identify your hot paths and fiercely protect them from heavy state mutations. Keep the heavy lifting out of your loops. Rule 2. Ruthlessly hunt down and eliminate any redundant vault trips, those SLOAD and SSTORE operations. Rule 3. Default to caching persistent state variables into local memory before you start calculating. Now for a quick reality check. Modern Solidity compilers have optimizers built in. They actually try to spot these patterns and apply caching automatically. But compilers are inherently conservative. They will not catch everything. Assuming a compiler fixed all your inefficiencies is a dangerous way to write code. To be absolutely sure, you need to use local gas profiling frameworks, like Hardhat or Foundry, to benchmark the exact amount of gas your functions consume. Trusting the compiler is a good start, but manually verifying your opcode execution is what separates average coders from elite Web3 engineers. In our next lesson, we will look directly at the receipts. You will learn how to open up actual opcode traces and hunt down heavy instructions, line by line. This video was created by Forge College. We build educational resources to help developers understand exactly how these systems work under the hood. If you want to dive deeper into EVM mechanics or explore other advanced Web3 topics, head over to forge.college. Because mastering gas mechanics is the best way to ensure your smart contracts are economically viable for the real world. Thanks for watching.